So many thanks to the organizers for the amazing opportunity that it is to give a talk here. And I decided to prepare quite an elementary talk, actually, hopefully elementary enough. And another point about this talk is that I think I under-prepared for this talk. I mean, not that I did not prepare for this talk, but there's less stuff than I could speak in 1 hour, because I'm actually expecting some questions and some discussion times. And also, if you have any questions, do ask it. Do ask them. Okay. So, as I said, I'd like to start things really elementary. So, let's. Oops, not a good color. Sorry. So let's N be a non-negative integer. So for the rest of the talk, and then TQFT is a functor. Let me call it F from N. Maybe I should write N plus 1 hob into vact. More so that I can say, so my definition of N is a dimension of space, and N plus 1 is a dimension of space-time. And when I say a functor, I really mean a honest functor. So I'm not thinking about infinity one categories, I'm really thinking about categories and functors. And perhaps I should just draw the usual diagram, just so that I can also fix notation. The main point here is that I have a gadget that given a manifold X and a manifold Y and a coordinate between them, which I'm actually always going to write down like this. So M goes from X to Y, returns something going from F of X to F of Y, which I'm going to denote as F of M. By the way, TQFTs are not, coordinates are not just defined by this diagram here. I always need to think about some inclusion of the boundary manifold into this side and on this side. So actually I should always see coordinates as spans, but I'm not going to go into this today. Okay, anyway, this is the point of view I would like to have today. And probably I should also say that this should be symmetric monoidal functor. Right, so this is the initial point. This is quite an old definition, the definition of the TQFT and the category of manifolds and coordinates. But perhaps, hopefully this is the trick worked. Yes, so there's no shadow, something that went well. But also say that the N plus 1, N plus 2 TQFT is a bifunctor from N plus 1, N plus 2 cob into, I'm just going to call it Alge. And when I say algebra, let me say some algebraically defined bicategory, which I'll make precise in a few minutes, hopefully. But now let me just quickly explain what this N plus 1, N plus 2 code should be. So I'm just going to draw like the usual diagram or the usual drawing of what these things are. So, okay, I'm not messing things up yet. So I could have a diagram like this, right? A drawing like this. Can everyone visualize this? So I have a manifold X here, which consists of this bit here and this bit here. And downstairs, I have again the manifold X consisting of this thing here and this thing here. On the right-hand side, I have a manifold Y, which, because I don't want to have too much work, is going to be the same as X. Then I have a coordination between x and y, which I will draw as n. I have another coordination n from x to y. And finally, this two-dimensional region is an extended coordination from the top coordination to the bottom coordination. Okay, so the rule is that I will draw these things globularly. So I should read this in the following way. So I have a one-dimensional coordination n from x to y, another one-dimensional coordination n from x to y, and connecting them, I have two-dimensional coordination, which I'm going to call w. Okay, so importantly, these things compose horizontally, these things compose vertically, so it makes sense to write down this type of globular diagrams. Okay, everything fine so far? Right, so I sort of sketch what this thing means. And by the way, the definition is actually quite messy if you actually want to look at smooth structure and do everything really correctly, really specifying the unit terms, really specifying the symmetric nodal structure. It's actually quite a mess if you want to do it with all details, but lots of people have checked it and it works. I explain what this is. Let me explain what this is today. So today, nope, the way around. So today, out this bicategory is going to be prof, also known as this, which is the bicategory of categories of profunctors and natural transformations between profunctors, albeit everything over vect. Let me quickly explain what this is. So objects, categories, usually write it as G, G, H, etc. So one arrows, usually denoted like this, G to H, and then this should be an F. In this case are functors. So F from G up times H, and let me write it as that. Okay, it's a bit like the word bicategory. Let's do it from the point of view of profunctors. So G and H are categories, and the natural way to go from the category G to the category H is via what's called a profunctor, which is, in this case, functor from G up times H into that. So the figure, if you want to have something in your mind, so if I have two objects, if I have X in of G and Y in of H, this is sent to something I'm going to call F XY, which is supposed to be a vector space. And the profunctor property says that if I have X prime and Y prime and an arrow gamma from X prime to X and another arrow phi from Y to Y prime, I should be able to get a linear map from, given my conventions, I think this is what I get. Might be the opposite, something which I'm going to call F gamma phi, which is a vector space map from top to bottom. Okay, so objects are categories, arrows are functors, and two morphisms are natural transformations. Etc. So this is actually quite an old bicategory. In fact, I believe this was one of the examples of bicategories in Benedlu's original papers on the definition of bicategories. It's a beautiful bicategory and actually very easy to work with. If you prefer to work over the Morita bicategory of algebras, bimodule, and bimodule maps, just note that given a category, I can linearize it to obtain an algebra, and then the profunctor naturally turns into a bimodule, and the composition of profunctors as well behave with respect to the composition of bimodules. In fact, I should have actually said what the composition of profunctors is. So given a profunctor f from G to H and the profunctor f prime from H to K, the profunctor f bullet f prime, which is the composition, is a profunctor such that given an object of G and an object of K, returns this object here. Right, so this is the way to compose profunctors. Let's do the more or less obvious end. I prefer to think of it as the tensor product of the bimodule given by F and the bimodule given by F prime over the algebra you get from H. And because I said I would be as elementary as possible, let me just quickly say what this is. You do the sum over all H's in the objects of H of fxh tensor f of H. Sorry, it should be a y set here. Okay, and then you need to divide by a certain equivalence relation, which probably I should not write this down. Find any book of category theory. Okay, it's very similar to the equivalence relation you use when you do the tensor product of bimodules over an algebra. Right, so where was I today? Yes, so I would like today to speak about extended, so n plus 1, n plus 2 TQFTs, also called once extended TQFTs, from the bicategory of n-dimensional manifolds, n plus 1 dimensional cobordism, n plus 2 extended cobordism to this profunctor bicategory. And the question I would like to sketch today is, can we define such bifunctors f from n plus 1, n plus 2 cob into prof, a bit from first principles. And the answer is yes. In fact, this is, I think, very related to the talk of Konstantin Telemann yesterday, except that Konstantin was looking at extended TQFTs using the cobordism hypothesis. I'm actually going to look at it from slightly more pedestrian point of view of how to define these bifunctors, just by using, I think, elementary homotopy techniques. Okay, right. So, how should I answer the question? Yes. Oh, this should be the other way around. Good. There's something else here I can use. This is visible. Good. So Yes, so how to define those Fs? So maybe I'll start by a quick reminder. This is actually the powerhouse for this. So it might seem elementary, but really, believe me, it's the powerhouse for the 1/6 TQFT and likely for the fully extended TQFT if you want to do it by pedestrian techniques. But it's the following. So consider a fibration. And when I say fibration, I really mean a Hurwitz fibration. So P from E to X. So E and X are at the moment not related to the manifolds and cobordisms. So anytime I have a fibration, which I'm actually going to go like this. So I have X and I have here my E. So anytime I have a fibration, I can define a functor, which I'm going to call OP, that goes from the fundamental groupoid of X. This is a fundamental groupoid, which I'm going to write as if it was the fundamental group. And it runs in category of topological spaces, not maps between topological spaces, but homotopy classes of maps between vector spaces. And the idea is that I send a point on the base to its fiber. So I send X to EX. Okay. And if I have a path gamma from X to Y, the homotopy lifting property of the fibration then gives a map like this. So if I have path gamma from X to Y, then the homotopy lifting property of the fibration immediately gives a map. Let me call it E gamma from the fiber at X to the fiber at Y. Okay, I'm going to call it whole because this is the holonomy of a principal fiber bundle. It's just an example of this. But here this is just defined up to homotopy. Fine, everyone? Right, so again, these are very basic homotopy theoretical techniques. And right, just a micro observation I would like to give is the following. So suppose right, like this. So let's consider two fibrations, E and E prime. So from space E prime with the same base space. Okay. And my question to all of you is that how would you compute the set of path components of the fiber product over X? So I should not have used the modified change it to an M because I should not have used X here. Right, so how would you know to compute the set of path components of this fiber product? It's actually quite a nice computation, and this boils down to the coend M in the fundamental groupoid of M, and then you need to do the fundamental, you need to do the path components of E at X on the path components with E at, well, sorry. So observation, if you want to, so there is this action of M on E and E prime by homotopy, up to homotopy, which then gives, well, a functor from fundamental group of the fundamental groupoid of the base to the category of sets. Well, there's this point here in which you actually need to invert one of the actions, because you should make functor on this side covariant, functor on this side contravariant, but no problem here because you can invert the direction of arrows on groupoids, and well, complete this coend, and you get exactly the set of path components of the value product. So quite an elementary calculus. I'm not going to say elementary, but something that could be given to write, well, average PhD student. Maybe note something here is that we're actually losing a lot of information in this process. So I actually started with this really ultimate functor from the fundamental groupoid of the base to category of topological spaces with maps up to homotopy, and I just passed on to path components of fibers. This actually can be categorified slightly, actually in a number of ways. And my take is that this is actually the multiple categorifications of this fact here actually help us do this fully extended version of the TQFT I will speak about today. I'll get here later on, but let's really stay in the absolute simplest case, which is the fundamental group of the base acting on the path components of the fibers, which already gives quite a lot of fun things. Right, so what should I do now? I should probably send this up. No, wrong. Oh dear. Right. Okay, this scene. So. Right, so let me then quickly write down a 1/6 TQFT based on these more or less elementary observations. So there's another piece of data I need. Can you still read? The whiteboard is a bit wet. Actually, too wet. So the other piece of data I need is a homotopy finite space. B. And when I say homotopy finite space, I mean a space with finitely many path components, each of which with finitely many non-trivial homotopy groups, all of which are finite, which was the definition given yesterday. So B is a data I need to define a 1/6 TQFT. It's a space with finitely many non-trivial homotopy groups, all of which are finite, and also finitely many path components. By the way, so given homotopy finite space B, there's this beautiful homotopy Euler characteristic, which is also called homotopy content. I think it appears in several different references with different names. And what you do is that you sum over the path components of B. Then you do divide by the cardinality of the odd homotopy groups. Sorry, making a mess of the whiteboard. Blackboard. And on the top, you put the other path components, the other homotopy groups, etc. Right, it's quite a beautiful computation with the homotopy finite spaces. And there's one thing which I like to call like the miracle property, which says that if P from E to B is a fibration of homotopy finite spaces, then I can compute the homotopy content, which is this computation of the total space, just by summing the all x in the path components of the base. And then you need to do the homotopy content of the fiber at x times the homotopy content of the path component of x in B. Anyway, believe me or not, this spherical property here, I don't know which it's due to. I believe maybe to Kontsevich, and the proof is actually quite simple. You just need to apply the wrong exact sequence of the fibration and apply it to a scopic computation, and this comes out. It's not immediate. There's a few things that still need to be said, but it's again boils down to simple enough homotopy theoretical techniques. The other bit I need to compute this once extended TQFT is the fact that the path components of the fiber product can be computed as the coend of the action of the base on the path components of the function space. By the way, I mean, I could also write down, maybe I should actually do this here. Sorry, making a mess here. Or perhaps this is actually not what this thing is not what I need to do the extra TQFT. Actually, it's something generalizes it slightly that says that if you have this situation here, then chi pi of the fiber product can be computed as some elements on the base or components of the base, and then you need to do chi pi of the x times chi pi of the x times chi pi of the path component of x in.
Sorry, that's not readable.
Pardon?
You need to put it up a little bit as this one, yeah.
Better?
Yeah.
Sorry.
Should one of them be E prime?
This should be E prime. So I'm actually concerned about the shadow here. So either the people in Harvard don't see or you guys. Anyway, so please believe me, with these two things are enough to build once extended TQFT. I mean, just by using a few other facts. I mean, if you see this really works very well with concatenation of cobordisms or competition of cobordisms. It's here. Good. Right. So then how is it that we are going to build the once extended TQFT? It's more or less done. And then let's see how it can be computed. And also possible generalizations. Right, so long chalk. So let B be a homotopy finite space.
Move up the top left border.
So I claim there is symmetric monoidal bifunctors. So FB from n plus 1, n plus 2 cob into off, which depends strictly on B. Again, this should be heavily related with the talk of Konstantin Telemann yesterday. It's quite inspired by this work as well. So, and how do you build this? Right, so you need to send an n-dimensional manifold to a category. So if X is an n-dimensional manifold, I wish I did not. Okay, so if X is an n-dimensional manifold, you send it to the obvious category you think about. So you have a homotopy finite space. We have a manifold, so we can build the function space of maps from X into B. Okay, and then compute the fundamental groupoid. It's like God given. You think, okay, if you wanted to find once extended TQFT values in the categories, profunctors, and natural transformations, starting with a multi-finite space B, you'd think, okay, let's just look at the fundamental groupoid of the function space. Good. And now I also need to say where the cobordism is sent to. So this is B. A sensible person would also put an n here to indicate which dimension we ring, but this works in all dimensions. Right, so what is a cobordism sent to? How should I write this down? Maybe like this. Okay. So I need a machine that does the following. So this is, I believe, my starting point. Okay, so I need a profunctor from pi1 of fundamental group, from the fundamental groupoid of this function space to the fundamental groupoid of maps from Y into B. So things like this. So in particular, such a diagram must be sent to a vector space. And again, the vector space is probably not given. So we would consider the space of all of these cages from M into B that extend F and extend G. Okay. So I would like the space of all cages that make this diagram commute. Okay. And again, I want to land in a profunctor. So for the moment, this is space, not a vector space. So the idea is to do the set of path components. And there you go. So that's the only simplest thing we could do. Okay. So the idea is that, so given an object of the fundamental groupoid of the function space of X values in B, given an element of the fundamental groupoid of maps from Y into B, I send this to the set of path components of the space of maps from M into B that extends F minus G. By the way, this is a homotopy finite space. It's a beautiful thing about homotopy finite spaces that if this space is homotopy finite and this one is a CW complex, then the function space is always homotopy finite. And if I consider the restriction of elements of the function space on that have certain values on a subcomplex, this is also a homotopy finite space. Things work quite well. And again, this falls down to quite simple homotopy theoretical techniques. Right, so I explained where the objects of this fundamental groupoid and this fundamental groupoid go to. Maybe I should say, so a profunctor also has, well, there should also be a way to make paths in this function space give rise to maps, or actually vector space maps between these sets. And I think the idea, maybe I should explain it like this. So because the inclusion of X into B is a fibration, if I'm able to slide F to F prime by using a homotopy, then I can slide this homotopy all the way to the function space. Just using the fact that the inclusion of X into N is a cofibration, so I can always extend these things, and this is the idea. Or you can just use this idea, because restricting a function on M to a function on X and a function on Y is a fibration. So immediately I have this functor from the fundamental groupoid of the base to top. Again, more or less basic homotopy theoretical techniques. Right, so if I wanted to prove this was a TQFT, what else do I need to do? I need to prove that profunctors compose well with respect to concatenation of cobordisms. And by the way, this follows exactly from this property here. Yes, exactly here. Okay, just believe me, just follows from this if you just use the right fibration. Okay, it's not completely trivial, but it follows more or less trivially. So follows from star, which is this thing here. And what else do I need to say? Yes, I should also say what I do to extended cobordisms. Note that up to now I did not use the fact that B was a homotopy finite space. B could be any space. Okay, all of this computation would work if B was any space, but if I want to actually have maps between, well, if I want to have vector space maps assigned to extended cobordisms, I need to have a homotopy finite space there. And what do I do?
Can I ask about the objects are linear categories, right?
Yes, so the idea is that you have a groupoid and you apply free vector space to the set of morphisms.
Okay, right. And the blue category of the walls you describes, I guess it has adjacency.
Yeah, it's just reverted.
Right.
So if you have a functor, because groupoids are, well, have a natural inversion, it doesn't really matter which side you go.
Right.
But again, these things should be observations coming after we prove we have had extended TQFT, because this extended TQFT is coming out from first principles. It's actually quite a nice playground to test conjectures. It's actually was one of the main reasons why we started writing this thing. Good. So where was I? Oh yes. So what to do with extended cobordisms? Now it's just the formula, which probably I will regret writing it down. So this would be one extended cobordism. Right, so this is the picture of an extended cobordism. I've actually raised the drawings. Yeah, I didn't erase the drawings. Sorry. Right, such a thing should be sent to a certain natural transformation of profunctors. Maybe I should just write down the matrix element. So I have this FP of W, which should be a natural transformation between profunctors. And I'm just going to write down its matrix element. So I have a H and I have H prime. Okay. And the idea is that H should be as what I have here. H prime should also satisfy the same relation, but now with respect to the cobordism N. Right, so I need a number to be assigned here. And now, so it's just not particularly illuminating. I need to consider the space of all maps T from W into V. I'm sure I'm going to run out of space. So space of maps T from W into V. Now I need to consider a certain commutative diagram, which I think it's this diagram here. So maps from T to B. With restriction to M is H, to N is H prime. And there's actually yet another condition I need to satisfy. I need to consider here X times X disjoint union Y times I, which includes here. And the condition is that if I go like this, I should get F disjoint union G. Not particularly illuminating, but that's what you do. And actually finding the right formula to put there was actually quite a nightmare. And of course, because I'm working with homotopy finite space, I always need to put this homotopy constant chi pi. And again, it's not too hard to see that space of maps satisfying this will be homotopy finite, so it makes sense to compute its homotopy content. Good, so I have no idea how much time I've already used. There's no clock here, is it? Oh yeah, thank you. So I've used 45 minutes, is that correct? Good, I was looking for the clock over the test. Yes.
I think at the beginning you said that this is a first principle construction, and now you just said something about 9.
Right, so this construction is sort of God-given, but there's actually lots of variants you can take here. So what's the right function space to use? This is hard. And actually proving that this thing here is a natural transformation of profunctors is more or less easy. Proving this natural transformation of profunctors is well behaved with respect to the horizontal composition of cobordisms. It's an argument that took me 1 month. Actually, I should have said this is not only my words, which are gentle with T. Porter, but took us maybe 1 month to actually figure out the right argument. It's tricky. It's all based on this beautiful identity that the homotopy contents of a fibration, of those special vibration, can be expressed as homotopy content of fibers, but to actually be able to use this, it's tricky. It's easy to see it works after you have the right formula, but it's not too basic. So first principles doesn't mean it's going to be everything is going to be easy, but it works. Anyone wants to ask something? Yes.
So if you restrict to groupoids and you look at the homotopy content,
Yeah.
then this looks like what's called like cardinality of a groupoid, etc.
That's correct.
And I mean there's a
generalization, if you have, say, some kind of something structural like a Lie groupoid will consider integration over these. And in the case of the discrete one, it recovers as kind of as like a counting type measure.
Yes.
So from that perspective, I've often wondered when I'm looking at these finite spaces, if there's a way to, if there's a 6-functor formalism lurking in the background, such that like you're taking like the dualized and complex, and then like so you're essentially like this formula come from like fiber integration.
Yeah.
And that formula is not. I think like this.
Don't know. Maybe discuss others. There's still like a few things I'd like to say.
Oh, I'm sorry. I thought you just mixed.
Sorry, no, I've not finished.
My apologies.
Yes, sorry. I don't have a very hectic style, I think, when I give talks. So now I need to figure out what I should erase. Maybe I should erase this side. And now the main thing to ask is how to compute this. Or can we compute this once extended TQFT? The answer is yes, or almost. So the answer is always yes, but might be harder in one case than others. So how to compute FP? So the idea is to pass to algebraic models, combinatorial models for homotopy. For example, we could do this computation in finite time by using, for example, simplicial set. So G, if G is a finite simplicial group, we could prove that okay, we would know that f of the W bar of G. So if you have a finite simplicial group, you do W bar, you have a homotopy finite space. And you immediately conclude that f W bar of G could be computed by doing the simplicial set of maps from X into W bar of G, and then simply computing the homotopy, the fundamental groupoid. This would be like, this can in theory be done in finite time, but still messy.
Sorry, I missed what is the W bar, like on the left-hand side and on the right-hand side. So G is a finite simplicial group.
So think of it as the simplicial classifying space.
Okay, this is.
Yes. It's the left adjoint, the right adjoint to the loop group construction. Right. So it's still messy, though it can be done. Can be done like finitely because this is a Cannes complex, and computing homotopy groupoids of Cannes complex is actually easy enough. But there's a much simpler case where we use two groups to model spaces. Okay, so I'm not going to be able to model those spaces. In this case, I'm only going to be able to model spaces with trivial homotopy group at levels greater or equal than 3, but this is still quite an interesting case. And anyway, maybe I should just say what the idea is and just write down a few formulae. So the idea is that we send X to the internal Hom, sorry, in the category of two groups, CRS, because I was actually thinking about cross modules. You do the Whitehead cross module of X, and you land in G. Right, so my two group is now a G, and this thing here is the internal Hom in the category of cross modules. And then I'll need to consider the fundamental group. Right, so quick result that comes out of here is the following, I would say. What should I erase? So immediately we have this interesting fact. I mean, it doesn't surprise anyone. I'm sure it's a particular case of someone that has done before. So consequence. So if G is a finite two group, there is a 1, 2, 3 TQFT sending S1 to fundamental groupoid of CRS I of S1 into G. Actually, comes from free from this construction. So, for example, if G is a honest group, this is just the extended TQFT, which sends S1 to the quantum double of the group algebra of G. You need to do this by conjugation. Right, so this lots of results came out of this. Let me just say, and by the way, let me be adamant, this cannot be explicitly computed because this Whitehead cross module, actually this Whitehead cross module in this case is just Z because the fundamental group of S1. This Whitehead cross module it's actually quite easy to compute. So these things can be done just with the hands, just on the fly. So another example, there is a 2, 3, 4 extended TQFT. And what would it do? So for example, if I would start with a group, actually with a cross modules of groups. So it would send S2 to, I think in this case, you need to consider curve of partial, and then the reaction groupoid, and actually that's the groupoid you send S2 to. This can be computed just extremely easily. In fact, it's I would be surprised if it's not a particular case of things. Right, let me just say.
It's when you put a genus G surface here instead of.
So the point is that this in the case of 1, 2, 3 extended TQFT, you just need to know the value of S1. But this is actually a mess because I did not wipe the blackboard, sorry. In this case, you'd actually need to build the, you need to build the vector space you associate to each surface just by considering the CW decomposition of the surface, consider the Whitehead cross module, and then considering the internal Hom mapping to G. There's no obstacle. It can be done more or less easily. It works. So good. So other things I would like to speak. Yes. So why is this clearly the beginning of something? Right. There's a place where clearly we are losing information because initially this is a two category. And I truncated the category, the two category to a category. So clearly losing information somehow, somewhere, but it's just the tip of an iceberg because hopefully without too much hassle using the same type of homotopy theoretical techniques, this can be twice extended, and maybe I should now stop here. But I can maybe say, I mean, there exists a there exists a 1 to 3, 4 extended TQFT, sending S1 to this two categories. It follows more or less by the same type of constructions. Modulo some things that you need to believe, because if someone knows the other reference that constructs tri-category of two categories, bimodule categories, profunctors being such a natural transformation, please email me, because I did not find any reference that actually does it with all detail. Good, I should stop here. Thank you.